What a wonderful day for learning about mass spectrometry, mass spectrometers, mass spectrographs. I'm serious. Anyways, this is a cartoon. When you Google mass spectrometer and look at the images, you almost always find these cartoons because the machine itself is a little bit more complicated with a lot of wires and tubes and magnetic fields and stuff, so they kind of simplify it a little bit. Let's start the story over here. I guess number one. We inject a sample. It could be a sample of a pure element. It could be a sample of a mixture of compounds. It could be a complicated organic or biological sample. We ionize it then from just the molecules or just the simple unionized particles. We make them into ions, positive or negative, usually positive, I believe, so that they will be affected by the magnetic field. They travel from the ionizing chamber into the accelerating portion here, where the ions are accelerated faster and faster between the two plates. It just takes a split second. They emerge through a hole in the second plate, and they begin to encounter this strong magnetic field, although it's variable and probably not shaped quite like this either. But in any case, the charged positive or negative ions interact with the magnetic field, and it bends them in a path. And indeed, some of the machines are shaped like this, so that we see the ions bend around the glass tube. Looks like this particular sample was made of X, Y, and Z components. The X plus, the Y plus, the Z plus got bent differently simply because they weigh different masses, slightly different masses. The detector over here on the computer analyzes which components were which, and we can kind of work backwards based on the strength of the magnetic field, the charge we think we have on the ion, the speed at which they emerge from this plate. And is that it? I think that's about it. Interesting. Anyway, we can work backwards to get a good estimate on the masses of these individual parts. Here's a slightly more complicated but colorful cartoon about the same. Yeah. This one has a green component, a yellow component, a purple component. The sample starts out over here, gets ionized and accelerated between the two plates, makes it through the two plates, and we see here a series of electromagnets that affect electricity and magnetism are connected. They put a force and therefore acceleration in a curvy path on these components. Looks like, according to what they've drawn here, the magnetic field has been adjusted to allow only the detection of this yellow component. But as they slowly increase or decrease that magnetic field, then the purple one might become visible and the green one might become visible. Here's a question. What's more massive? Stream C, stream A is green, stream B is yellow, stream C is purple. Wouldn't you think C is more massive? Because it's not bent as much as stream B. And it looks like stream A is particles in this component, this part of the mixture in the original sample is the lightest because it gets bent the most by the same magnetic field. They have the same speed, approximately. It should be if they have the same charge in this area. This little cartoon is trying to describe how we might be able to notice differences in charges because a small positive charge is indeed bent toward the negative field. There's the negative electric field. So you can use an electric field or a magnetic field, but the single positive is attracted like so. The double positive is, oh no, wait a second, I better correct myself. I think they're showing the relative sizes in terms of mass, and not necessarily the electrical charge. So even though they've drawn this particle larger, it does not imply a larger positive charge. It implies a larger mass. So larger masses are bent less by the same magnetic or electric field as the smaller particles. Smaller particles are bent more. I could finish my original thought. If this was a +2 or a +3, how would it be affected in this magnetic and electric field over here? Well, the answer is a larger charge here would have more of a force and it would be bent more. So if I had the same mass as this particle but a 2 plus charge instead of a 1 plus, perhaps it would be bent twice as much to be right about here, to be equal with this one. Here's a mysterious thought. These mass spec machines are so common and so good. They can measure masses to fine detail. And it looks like this mixture has, oh my goodness, 1, 2, 3, 4, 5, 6, I don't know, more than a dozen, maybe 20 components. Although some of this down here might be arguably background stuff or stuff that might have been in the mixture that we cannot distinguish or say for sure what the mass was. This cartoon we have carbon 12 and helium 4, both singly positively ionized. Carbon 12 might be 3 times heavier about than helium 4 because 12 particles in the nucleus and 4 particles in the nucleus. 12 particles is 3 times more than 4. So having a bigger mass, a larger mass with the same charge would not be bent as much. So I'm gonna, oh there it is, they're telling us beam B, component B of the mixture was helium. It's bent less, no, bent more because it's lighter. There we go, said it right that time. Oh yeah. So the magnetic field certainly affects the degree of the bend, how much the deflection, increasing the accelerating voltage, so perhaps making the particles go faster or slower. That will of course also affect how much of a bend we experience. So even if we put a pure sample of neon, say for example, a noble gas, into the mass spec machine, it can indeed tell that there are different isotopes of neon. This looks like neon 20, neon 21, neon 22. So neon always has 10 protons in the nucleus, but sometimes it has 10 neutrons, or 11 neutrons, or 12 neutrons. Looks like it's very common, like 91%ish of the time, to be 10 protons and 10 neutrons. 8% of the time, 8.8% of the time, 10 protons and 12 neutrons. A very small percentage of the time, 10 protons and 11 neutrons. Interesting. And we can add up these atomic mass units for the particles, neon 22, neon 21, close to 22, close to 21, close to 20, based on exactly how much a proton and neutron weigh and such. The mathematical technique is to say, what's the average of 91% of this, almost 9% of this, just a small fraction of this. We change the percents to a decimal, so move the decimal 2 places to the left, and multiply by the AMU number. And so 8.82% times this mass, 0.257% times this mass, 90.92% times this mass gives me the total mass of each component. Add up the 3 components and we see the total averaged mass of this pure sample of neon, 20.164. These mass spec numbers can be very precise with very many sig figs. Interesting, a proton and neutron weigh almost the same, but not exactly the same. That was so much fun. Maybe we better do that again, just to make sure we got it. Look at another one. Here's a hypothetical sample of some element, doesn't say what. 35% has a 54.9 AMU. 45% of it has a mass of 55.8 AMU, and 20% of it has a mass of 56.8 AMU. Interesting. So what do we do with those numbers? Do you already know? You could try it. So reading these percents from the graph times the AMU number. Oh yeah, that was listed on the graph, correct? Yeah, it was on the x-axis, the AMU, atomic mass units. Interesting. Same story, 35%, 45%, 20%, and the relative AMU values, masses, mass of this component, mass of this component, mass of this component, and lo and behold, the average mass is about 55.7, although, which one's limiting here? Looks like the 20 point, looks like these percentages with the 3 sig figs were limiting, and I wanted to round my answer to 3 sig figs. So also, for example, the most abundant isotope of scandium is scandium-45, but the averaged masses represent, in a representative sample, that means a pure sample of scandium, 44.955910, might even be more than that. So what are the other isotopes of scandium that must have been included in this measurement? Would they be 45, 44, 43, 46, 47? Well, don't you agree, since the averaged mass came out to be less than 45, don't you suppose there should be quite a measurable number of scandium isotopes that are less than 45, like maybe 44, maybe 43? And I'm just waving my hands in the air, guessing at that, but it makes sense in a way. Sometimes I like to say, what's the average of 12, 12, 12, 12, 12, 12, 12, 12, 12, 12, 13, 12, 12, 12, 12, 12, 12, 12, 12, 12, 12, 112, 14, 12, 12, 12, 12, 12, a million 12s, and 13. And the answer is I don't know, because I just made that up. But you know what? I said so many 12s, I'm pretty sure the average would be close to 12. But every now and then I threw in a 13. I did throw in 114 as well. So those average of all those numbers probably comes out to close to 12.01 for carbon. I hope. I just made those up. Don't check me on it. Here's iron. Yeah, iron. Iron's 55.9 AMU on the average, 55.933. Which isotope of iron do you suppose is the most common? Well, if it has 26 protons in the nucleus, 26 plus 30 would give me 56. I'm thinking iron 56 with 26 protons and 30 neutrons in the nucleus. That comes out to very close to 56 AMU. But since this number is a little bit less than 56, I would suspect also some iron 55, maybe some iron 54. Here's a cool one. Check out helium. Its average mass is 4.003. So I suppose most helium atoms, isotopes, have 2 protons and 2 neutrons for a total of 4 AMU. But what would you suspect? There might be a few helium-5 or maybe even helium-6 isotopes to make the average a little bit more than 4. Alright guys, thanks for watching. See you soon.